Welcome to the One Source PH. In this video, you're going to learn about the atom. We're going to introduce some information about the atom starting with its history, some basic models that are proposed for the atom, and importantly, basic concepts about the atom. So way back even before Jesus Christ were born, there were philosophers that put forward notion about the atom. So one of them is Democritus, and he did this way back 460 BC. So he is a Greek philosopher, and he believed that the world, or suggested that the world was made up of two things, empty space and atomos. So this word atomos comes from the Latin word, or the Greek word rather, which is uncatable. Okay, and it has two main ideas. That is, the first one are atoms are the smallest possible particle of matter, and there are different types of atoms for each material. So the idea was abandoned, and it takes actually 2,000 years before a scientist in the person of John Dalton proposed again the atomic theory. That was back in 1804. So he said that all matter is made up of atoms, and atoms of one element are all the same. Atoms cannot be broken down into smaller parts, and compounds formed by combining of two or more atoms. And it says that Dalton's atomic model were like a billiard ball model, and he envisioned atoms as solid hard spheres like billiard or pool balls, so he used wooden balls to model them. So just like this. So this was proposed back in 1803. Research doesn't stop there because we do not know the dimension of the atom or if there are anything else that makes up the atom. So persons like or personalities of science like J.J. Thomson go ahead, went on and tried to discover more about the atom. So J.J. Thomson is the one responsible for discovering of the electron. So it was back in 1897 when he discovered the electron. So he was the first scientist to show that the atom was still made up of even smaller things. So a proof, the electron. So it is regarded as subatomic particles, but this is just the advent of the discovery, or this is just the start of the discovery of more subatomic particles. So electrons in 1897, English physicist J.J. Thomson, who lived from 1856 to 1940, discovered the electron. Electrons are negatively charged subatomic particles, and Thomson, in order to discover the experiment, the electron have performed the experiments that involve passing electric currents through the gases at low pressures. He sealed the gases in a glass tube fitted at both ends with metal discs called electrodes. The electrodes are charged with the positive and negative, and the electrodes were connected to a source of electricity. So technically, there is a voltage difference that are developing on the nodes that causes the electrode to become positively charged, and the other is negatively charged. So this is how the setup goes. So we have the positive side, all right, and this is the positive side, which is called the anode, and we have the negative side, which we call the cathode, and this is connected into a high voltage source. And when he set this up, he noticed a green light, or a light that is emanating from one of the discs. All right, so he concluded that this is negative streams of particles, and he called it electrons later on. So the result of the experiment is a glowing beam of cathode ray that traveled from the cathode towards the anode. So the cathode ray, or we can call it electron beam, is deflected when several arrangement of charge plates were placed nearby. All right, so there is a deflection when a negative plate is moved, all right, towards the ray, and it is deflected towards the positive plate. Thomson found that the cathode ray is deflected by the electrically charged metal plates, and a positively charged plate attracts the cathode ray, while the negative charged plate repels it. So, according to J.J. Thomson, there is a need for the remodeling of the older version of the model, which is the billiard ball model of the atom. He called his model the plum pudding model, which is just like this. All right, so there is a spherical cloud of positively charged particle, and its electrons are embedded in it. So Thomson knew that the law of charges, which states that opposite charges attract and like charges repel. So he hypothesized that a cathode ray is a stream of tiny negatively charged particles, which is moving at a high speed. So at first he called it corpuscles, and later on he called it electrons. So these particles are also affected by magnets. So a cathode ray can also be deflected by magnet as seen in the diagram. Alright, so if you're gonna buy your own cathode ray, you can actually conduct the same experiment and prove for yourself that it is affected by electromagnetism. Some older versions of the TV or television sets, when placed a magnet nearby, would actually create a certain um, distortion in the picture that is being produced in the picture tube of the TV. So that is a proof that this is affected by magnet. So J.J. Thomson went on and tried to describe the mass of the electron and the charge of the electron, but it was Robert A. Millikan, which is a U.S. physicist, born and lived from 1868 to 1953, who carried out the experiment and was able to find the quantity of the electron's charge. So he used the Robert Millikan oil drop experiment. So Millikan suspended negatively charged oil droplets between two charged plates. He then changed the voltage on the plates to see how this affects the droplets' rate of fall. So to his surprise, uh, from his data, he found out that the charge on each oil droplet was a multiple of 1.6 times 10 to the negative 19 coulombs, meaning this must be the charge of the electron. Using the charge to mass ratio proposed by Thomson, Millikan was able to calculate the mass of the electron. Alright, so Millikan's values for the electron's charge and mass are similar to those that are accepted today. An electron has a unit of negative charge and its mass is around 1 all over 1840 times the mass of the hydrogen atom. So meaning to say that the electron is 2000 times less dense or less massive compared to the proton or compared to the hydrogen atom. The plum pudding model were short-lived or is short-lived. So because back those times when subatomic particles were discovered, scientists are wondering how the particles were put together in an atom, because they know that charges are interacting with one another and positive and negative charges tends to attract one another. So it will take no time for the electron to bump to the and crush, okay? So meaning to say that the model seems to be not reasonable. So scientists, or most of the scientists during those times, including J.J. Thomson, believed of his model and thought it like the electron were evenly distributed throughout an atom filled with positively charged material. In Thomson's atomic model, known as the plum pudding model, electrons were stuck into a lump of positive charge, similar to raisins stuck in a dough. So here are some physical properties of the electron before we move on to the next and latest discovery and revision about the model of the atom. So the electron is found to have mass, and it's about 9.1 times 10 to the negative 31 kilogram, and its charge is 1.6 times 10 to the negative 19 coulombs. Alright, so one of his students, in the person of Ernst Rutherford, were able to contribute in the understanding of the atom. Ernst Rutherford is from New Zealand, and he was born back in 1871 and lived until 1937. He was also awarded of the Nobel Prize for Chemistry in 1908. And you can see his picture on the New Zealand $100 bill. So let us try to check his accomplishments. So he was able to prove that the atom has a dense nucleus, and he called it the atomic nucleus of the atom. Rutherford's gold foil experiment were able to prove many things. So in 1911, Rutherford and his co-workers wanted to test the existing model, which is the plum pudding model of the atomic structure. So they devised the gold foil experiment. So their test used alpha particles, which are helium atoms that have lost their two electrons and have a double positive charge because of the two remaining protons. So in this experiment, the alpha particles are directed into the gold sheet, just like this. So a source is emitting alpha particles, and we can see that there is a detector or a film right here, and alpha particles that pass through the film would be detected at the back, but there are alpha particles that bounce back, and that gives rise to his question. So there must be something in the gold foil that is so massive that tends to knock off the alpha particles, which are massive and have a positive charge. So meaning to say there is a strong repulsive force, or there is a strong and massive matter that is hit by the alpha particles that makes it rebound. According to the prevailing theory, the alpha particles should have easily passed through the gold foil, but this doesn't happen, with only a slight deflection due to the positive charge thought to be spread out all over the gold atoms. But they have seen that some of the alpha particles bounce back. So they're trying to explain the scenario or the result of the experiment and try to create a new theory for the atom. So based on his experiment, Rutherford have made or have proposed and have concluded the following things or ideas. So the atom is mostly an empty space. There is a small dense center with a positive charge, and that is the nucleus. At this point in time, the neutron is not yet discovered. It will wait a few years, and it will be Chadwick and Goldstein who will discover the neutron. So, but at this point in time, Rutherford concluded that there is a small dense center with a positive charge. Rutherford discovered the nucleus in the atom. So he proposed the planetary model of the atom, wherein there is the center of the atom is a positively charged particle. He called it proton, and the electrons are actually revolving around the atom. So in the latest version, actually the electrons were moving in a cloud. So that is a part of the quantum mechanics. And later on, maybe we'll have a brief introduction about the quantum mechanics. All right, so according to Rutherford's atomic model, um, the nucleus is a tiny, densely packed compared with the atom as a whole. As a result, the atom is largely an empty space. So this is compared to the size of a football stadium, and the nucleus is just the size of a marble that is placed at the center of the stadium. So you can actually imagine how big or is the space, how big is the empty space in an atom. Rutherford's model is seemingly incomplete because it needs to needs to be able to describe the chemical properties, and it wasn't able to answer why the electrons are staying in some orbit and it doesn't um, bump and hit the proton, because we all know that there is a electrical interaction, all right? So charge interaction between positive and negative charge. So the question now is, why does the electron does not bump the nucleus or the proton? So it goes to show that there is a need to revise and remodel the Rutherford planetary model, or add some key concepts to be able to explain the chemical properties of elements. So the next scientist that we're gonna talk about is Neil Bohr. To understand where the scientists are coming from, we should be able to understand the predictions that are laid by, are offered by classical mechanics about the atom. So since we have already know that Rutherford model is something like this, which is the nuclear atom, and we all know that we have a proton at the center and the electron is revolving around um, the nucleus. All right, so it predicts that the electron will actually lose or eventually lose energy, and we have some equations about that, and we're gonna show you that in the following slides. Before trying to derive Neil Bohr's formula and before trying to do some quantum mechanics, we should first try to describe the atom using classical physics. And so I have here a free body diagram. All right, so we're gonna write here of free body diagram of the electron. So F BD. All right, so physics students are or needs to know about the free body diagram. All right, so we have here a model of the hydrogen atom. All right, and here is an electron that is moving with a certain velocity around our nucleus, and we have a proton right here. Actually, we use positive E here because electrons and protons have the same magnitude of charge, only that they are different in their polarity. And we know that there is a force of interaction that is existing between the electron and the proton, and we call that F here. So that is electric in nature, so I'm gonna write Fe. All right, so this Fe is actually pertaining to the Coulomb's law. All right, so we're gonna write K here. So this is actually a constant of proportionality, charge 1 and charge 2. All right, so these charges respectively are the charges of the electron and the proton, and this is affected by the distance of separation squared. So this is r squared, right? And there are other formula that or this constant has some is expressed uh, in a lot of ways. And we have one for this. So K is what you call the electric constant or Coulomb's constant. And we can write that using an expression. Um, K is equivalent to 1 all over 4 pi. This one, EO, is what you call the, actually it's a Greek letter, all right? So let's write that letter legibly. Okay. So forgive me, I am a bit nervous using paint while discussing. And yes, I'm terrible at writing. All right, so we have the vacuum permittivity, and we can use this letter. All right, so EO. So EO is actually the vacuum permittivity. All right, so we have the formula for the electric force, which are present between the electron and the proton, and it is attractive. All right, so because we will see that we have positive times negative, so this is attractive. So there must be a negative sign right here before. All right, and in some instance, this negative sign tells you that the force is conservative. All right, and we know that if this electron changes its velocity, will not be able to maintain the force, and it will try to circle around, and a moment of time will hit. All right, will hit the electron. All right, so it will spiral inward as it loses its energy. This is actually due to the prediction of Maxwell that uh, an accelerating charge will eventually lose its energy, and it cannot counter the amount of force, the attractive force that exists between them. So theoretically, the electron should spiral inward and hit the proton rather. So that is the prediction of classical mechanics. We will try to relate the electrostatic force or electric force that exists between the proton and the electron to the movement of our movement of the two actually. So because the proton is vibrating, all right, and it's moving, and also with the electron. So later on you will see that the center of the mass of the system is not the proton itself, but maybe somewhere near. All right, so let's write the equation for the electric force. So which is Fe, as I've mentioned. So we'll write with the constant, electric constant, using the equation that we have derived earlier. So I have 1 all over 4 pi, all right? So vacuum of permittivity of space, and then R. So let's do another R. Write another R. Yep, squared. And here the charge is both the charge of the electron. So E times E is E squared. All right. So this is the electric force that exists between them. All right. So we're gonna relate the force of the electron to the Fc, or the centripetal force generated. All right. So since the centripetal force is equivalent to um, m v squared over r. So we're going to relate these two equations. So we're gonna equate the two equations and see if we can solve for some quantities. So let us try to simplify this two formula, and we can write the equation. uh, the new equation would be 1, all right, 1 all over 4 pi, um, the vacuum permittivity squared, r squared, all right, which is the radius. Yeah, you have E squared right here is equivalent to the centripetal acceleration, all right, which is mv squared um, all over r. Yeah, this one is quite not right, so we'll erase that. Yes. So you will see that you can actually cross multiply um, both sides by r, or multiply both sides by r. Okay, and you're gonna have one equation again. All right, so we can write that as 1 all over 4 pi the vacuum permittivity times E squared all over R is equivalent to mv squared. So we'll go back with or to this equation later on, but let's just put it um, somewhere that we can access later on. All right. So let's try to derive the formula for the angular momentum of the electron that is moving around the, the atom. According to Niels Bohr, the electron is situated in an unstable orbit. So there must be a condition. So one is there should be a stable orbit. So these are the only orbit that are allowed, which are distance away from the nucleus. All right, so to make this happen, so the electron seems to be rotating just like our planets. That's just like how our planets rotates or revolves around the sun. So and it should not change direction and whirl around towards the center. It must have, all right, an angular momentum that is fixed, meaning to say the angle between the velocity and the force must always um, be equal to 90 degrees, all right, and it means that the angular momentum must be um, constant. So that's one requirement according to Niels Bohr. So angular momentum has its formula. L is equivalent to the mass, all right, times the velocity, and then the cross product of the radius vector. All right, so this is equivalent to mv, or the momentum of the particle, all right, times r, or the radius vector. So now what we're gonna do is to try to express the angular momentum in terms of quantum mechanics. All right, so let's write the equation right here. L is equivalent to mvr. All right, so mv here is the momentum, and in quantum mechanics, this is related to the Planck's constant. All right, so we'll start with well, let's try to erase this first. All right, so in the 1900s, a scientist in the name of Max Planck were able to explain the black body radiation, and that the radiation emits an energy. All right, E is equivalent to HV. All right, so radiation R is not continuously emitted. All right, so it is emitted in steps, HV. So we have NHV. All right, so I hope that you can understand what I'm writing. All right, well, where H is equivalent to the Planck's constant. Planck's constant. So I do not know the spelling. Planck's constant. I hope I'm right. Yes, and then V is the frequency, okay, of the oscillator. So the electron has a frequency which is equivalent to the number of times that it circles around the proton or the nucleus. So there is where we get the frequency, and we can relate this to the momentum. So we have momentum P, all right, is equivalent to mv. So I'll write P here. Yes, P is equivalent to mv. All right, so this is equivalent to, according to Einstein, we have the energy and all over the c, which is the speed of light, and this is equivalent to this one. So we'll write it there. Oops. So I'll try to erase this. So I hope that you can follow. And that's n. So the steps at which the number of times the radiation or the energy is radiated. So in n steps. So the radiation is not continuously emitted, but only in allowed steps. So that's why the word. That's why we define the quantum physics like that. All right. So we can relate the two equation. We can rewrite it as P. Momentum P is equivalent to mv, and this is just equal to n times the Planck's constant times the frequency V all over c. All right, so I'm gonna erase this and rewrite again. So this time we are going to use the concept about waves. We have frequency, all right, is equivalent to, so we have F is equivalent to velocity all over wavelength. All right, so yes, so since this is velocity, we write V or over wavelength. So we're going to derive for the frequency. All right, so since this is actually the frequency, yes, so this is the frequency. So NC here is actually the speed of light, or we can call it the velocity of the electron. So we'll write here so speed of light and or velocity. All right, so we need something like velocity all over, or frequency all over velocity. So we need something like that, so that we need another factor so that we can substitute it here. So we'll start deriving from this equation. So let me show you. So I'm gonna erase this for a while and do the solving. Alright, so let's go back and use the brush. So you have the frequency here times the wavelength is equivalent to your velocity. Okay, and then we divide both sides by f. All right, or else or so we divide it by frequency. All right, and divide both sides by frequency. So we'll divide by f, divide by f, and rewrite this one again. All right, so let's go back so that I can show you better. All right, so there we go. B over f. All right, so and here is the frequency. So we need the reciprocal of this. So we raise this to -1. All right, so raised to -1, we're gonna have 1 over the wavelength is equivalent to f all over the velocity, which is equivalent to v up there all over c. So we'll use this factor and substitute it in there. So we're gonna see that. So we will see that this formula is just equal to n, which is the number of steps, all right? And h is the Planck's constant, and you have there your wavelength. All right, so the wavelength is equivalent to the path, okay, which is traveled by the electron. And in our case, the simplest orbit that can be allowed is a circle. So the wavelength there is equivalent to the path traveled by the electron, which is a circle. So it's gonna be 2 pi r. So we can write it as momentum p is equivalent to mass times velocity is now equivalent to n, which is the number of allowed steps, times the Planck's constant times the wavelength, which is now equal to n times h all over 2 pi r. So which is the circumference of this one. So we have a formula for momentum, or the angular momentum now for p is equivalent to mv. All right, is equivalent to n times h, all right, h all over 2 pi r. So if you're gonna cross multiply r, all right, to the other side, this will give you L is equivalent to r times p, which is this one. All right, this formula over here, and it will be equal to mvr, all right, is equivalent to n times h all over 2 pi. So that there is where Niels Bohr was able to conclude that it is constant, and the value of the angular momentum is equal to L. All right, so we'll write L here. All right, L. Oh my god. So yeah, it's difficult, and yep, L is equivalent to mv times r, and this is a multiple of n times the quantity of h all over 2 pi. All right, and this is constant. It's not changing for the hydrogen atom. All right, so we can still try to use this formula to know more about our atom. So let's try to solve for the velocity of our electron. All right. So yes. So we have v here for the velocity. All right, and that is equal to technically we're gonna solve it from here. All right, so we'll divide both sides by m all over r, mr rather. So we're gonna have n. All right, so that's the whole number times the quantity of h all over 2 pi. All right, and mr is here, so that is the mass times the radius. All right, so we can write it as v is equivalent to n times h, which is the Planck's constant, all over mass times 2 pi r. All right, so that is how we get the velocity, but we do not know the radius yet, so we'll try to solve for the radius. All right, so we can solve it using the equation that we have just derived earlier, which is the relationship between the electrostatic force or electric force and the centripetal acceleration that is felt by the electron. And we're gonna solve the we're gonna substitute velocity for that in v in that particular equation. So our equation earlier is k. All right, so we have k here, which is the electric constant squared all over r is equal to your mv squared. All right, so we have found out that the velocity is equivalent to nh all over mass times 2 pi r. So we're gonna write right here. So we have k e squared all over r is equivalent to the mass. All right, and we're gonna square that, so we're gonna put it inside a parenthesis, and we have n times h. All right, all over mass times 2 pi r. All right, and we're gonna square that, so you will see that we can readily cancel this one, okay, after we distribute it. So we're gonna have k squared all over r is equivalent to mass, okay, times n to the power of 2, h to the power of 2, m to the power of 2 times 2 raised to the power of 2 is 4, and then pi r, pi squared. All right, r squared. All right, so there we go. So I hope that I did it right. So 2 squared is 4, pi raised to the power of 2 is pi squared, and then r squared. So this one will cancel. All right, so we can also cancel that one, and upon multiplying both sides by r squared, you will see that one r will cancel out. All right, so this one will cancel, minus 1, and then this one will cancel out. So what remain is k e squared, all right, is equal to rke. All right, so because we multiply that r there, we have n squared h squared all over 4 pi squared r squared. All right, so we have mass underneath, so we multiply this by m. All right, so let's write that equation. So we write the equation over here, and we know that we have a value for k, which are also all constants. All right, so we can write it as 1 all over 4 pi. All right, so let's make that straight. All right, so 1 all over 4 pi EO, all right? And that this is multiplied by E squared, all right, times R. So this is all over 1. All right, this is equal to N squared, H squared, and then we're gonna have 4 pi squared, and then times the mass. All right, so we know the electron mass, so we can actually do some arithmetic here. So, or algebra rather, we can cross multiply 4 pi squared on the other side, and we're gonna have 4 pi squared all over 4 pi EO, all right, times E squared times R all over 1 is equivalent to N squared H squared all over M. All right, so this thing will cancel out. All right, 4 divided by 4 is just 1. Pi squared divided by pi is pi, and over EO times this 1. So we can simplify this as, all right, so let's simplify it. Don't save, and then we'll open up a new, oh, this was lost. All right, so we're right. Yeah, so it's clean. So I hope I didn't forget that. So we have pi. Uh-huh. All right. So let's try to write the equation again. We'll start with pi. All right. So I hope I can write it as good as you do. All over the vacuum permittivity of space times e to the power of 2 times the radius all over r, all over 1 rather. All right, so all over 1 is just equal to n squared h squared all over the mass. All right, so here we can divide both sides and by this factor, all right, and solve for r. So we have r, or the radius, is equivalent to n squared h squared all over mass, all right, times cross multiply this one, so it's gonna be on the numerator. We have EO all over pi, all right, times the charge, all right, E squared. So this is your new formula in finding the radius. So using the formula that relates the electric force and the centripetal force, you can actually find the velocity. So you can just use Fe is equivalent to Fc, and you can derive for the velocity there. So right now we know that the atom as a whole has its energy. All right. So, and we know that it has two parts. We have the potential energy, and then the plus the kinetic energy. So it has two parts. So the potential energy is given by the electric force that are existing between the proton and the electron. So the kinetic energy is given by the movement of the electron, and this thing is actually moving as a whole. So we need to do some calculation to tell the total energy of the system. So basically we have E, all right, E is equivalent to PE, right, plus KE. And this is just equivalent to 1/2 mv squared, which is the kinetic energy, but uh, there are other equivalent forms of that when we are talking about the atom. So we will continue with the derivation of the formula as we try to find the total energy of the electron. All right, so the total energy that is holding the electron of the hydrogen atom in its orbit. So we have E is equivalent to um, yep, E is equivalent to PE, or let's say for example KE, um, to arrange it properly, plus PE. All right, so we know that PE is negative potential, so we're gonna affix the sign there, and KE is just equivalent to 1/2 mv squared, and then this thing here is actually the velocity, which will be yeah, revealed later on. So we're gonna have, since I told you that PE is negative, so negative times positive is negative. So and this is equivalent to the electric potential, which is given by E squared, all right, or um, K, all right, E squared all over R. All right, so this is the one equation for the total energy that holds the electron of the hydrogen atom in its orbit. We can also rewrite this as where's that? Where's my pen? Okay, so E um, is equivalent to 1/2. Okay, so that's not 1/2. So 1/2 mv squared, all right, is equivalent to K, a minus rather, minus 1 over 4 pi, and then times the vacuum permittivity EO times E squared all over R. All right, so, and then we have a formula for the velocity, which is V is equivalent to, all right, so that's equivalent to E, all right, so that's the fundamental charge. So where's that? So here, yep, right, some fundamental charge, which is 1.6 times 10 to the negative 19 all over the square root of 4 pi EO, or the vacuum permittivity, times the mass times the radius. So that's gonna be 4 pi, then the vacuum permittivity times the mass times the radius. So this is the velocity. So we need to square that, and this formula will look like E is equivalent to 1/2 times the square root of, yep, the mass. All right, so we're gonna put the equation for the velocity inside this one, and we'll square this E, and then we're gonna have 4 pi EO, all right, times the mass times the radius. All right, so minus the potential energy, or the electric potential, which is 1 all over 4 pi the vacuum permittivity times E squared all over R. All right, so you will see that we can distribute the exponent. So we're gonna have 1/2 times the mass. All right, so e to the power of 2 is E squared. So we'll write E squared there, and then the square root will cancel out, so you can write 4 pi vacuum permittivity, EO, times the mass times the radius. Alright, so close that, minus 1 all over 4 pi this one times E squared all over R. Alright, so you will see that the mass will cancel out. Alright, and it seems that they have the same denominator. Alright, so we can actually simplify that. So we can simplify this by following the rules and simplifying fractions. So you're gonna have where is that? Where's my pen? Alright, so E, or the energy, is equivalent now to, yes, this one, but we'll write it as E squared, alright, all over 8 pi EO times R. So minus, alright, so here we're gonna multiply it by 2, alright, so that it will make it the same, pi EO, alright, times R. So we're gonna multiply the numerator by 2, and we're gonna have this one, 2E squared. So we're gonna have 1 minus 2 is negative 1. Alright, so we're gonna have negative E to the power of 2 all over 8 pi vacuum permittivity times R. So this is the amount of the energy that is holding the electron of the hydrogen atom in its orbit. So if you want to remove that electron there, you have to outmatch this energy. So if you pull the electron with a greater force or a greater energy, greater than negative 13 electron volts or negative 13.5, so you can actually check that, guys, no? And yeah, so this is around negative 13.5 electron volts, negative 13.5 EV. So you can try to check this value by plugging it in, or plugging the values for pi and the vacuum permittivity and the radius. Alright, so this is what you call the Bohr radius. Alright, so Bohr radius. So there are a lot of things that happen in this presentation, but we're not done yet, believe me. So as mentioned, the hydrogen atom has only one electron, but there are many elements that contains many electrons, and Bohr cannot explain. Okay, so that means that his theory is lacking something, and therefore there is a need again for reviewing and revisiting or revising the Bohr model so that it will fit the observed phenomenon among elements. So all that is missing from Bohr was provided by, or was answered by Schrödinger, okay, with the wave equation that can describe the many electrons of our atoms, and it yields fruit with the quantum numbers. So here are there. So we have 4 quantum numbers. 3 of them are trying to locate the electrons. So let's study them. So quantum numbers are required to describe the distribution of electron density in an atom. So basically, we cannot tell 100% where the electron is at a specific moment in time. So the more we get so accurate about the location, the more we do not know about the energy. So this is about the Heisenberg uncertainty principle. So therefore, this is just a distribution or a probability function where we can find an electron at a specific point in time. So this is a space of probability. So that's why Schrodinger is very controversial in his results, but nonetheless, it's able to predict the behavior of the atom. So first one is the atomic orbital, which is the one that is found by Niels Bohr. So congratulations, Niels Bohr, for that. So we call that the principal quantum number n, and it designates the size, so how big the atom. So this is otherwise known as the energy level. All right, so it counts the number of shells. All right, so in the periodic table, this pertains to the groups. All right, the horizontal groups. So period 1 to 7. So that is the principal quantum number, and the next one is the angular moment quantum number L, which describes the shape. All right, and next is the magnetic quantum number ML, which specifies the orientation. The fourth quantum number is about the spin. All right. So the principal quantum number n designates the size of the orbital. That means larger values of n corresponds to larger orbitals, means to say more electrons. So the allowed values of n are only integrals, so 0 is not a part of it. So we have 1, 2, 3, and so on and so forth. So the values of n corresponds to the n Bohr's model of the hydrogen atom. A collection of orbitals with the same value of n is frequently called a principal energy level or shell. Alright, but there are rules on how the electrons behave. Alright, so actually electrons pair up by twos. That means higher energy levels would have to find a place where to place or distribute the extra electron. So there is a need for the second quantum number, which is the angular moment quantum number, which describes the shape of the orbital. So the values of L are all integers that depends on the value of the principal quantum number. Technically, there is a formula for that, and the formula is n minus 1. So from 0 to n minus 1. So here, 0 is always included. Alright, so for example, if n is equals to 2, L can be, we follow n minus 1, so we have 2 minus 1, we have 1. So from 0 to 1. Alright, or can be 0 or 1. 0 is has something to do with the s suborbital, and yes, so basically it's the ground state. So all of those that are in S are the ground state. So they are the lowest energy level. So this is the orbital designation. So if you're gonna have 0 as L, that's your S designation. And if you have P, alright, so L equals 1, you have the P, so you have the S and P suborbital. So if you have L is equal to 2, you have the S, the P, and the D suborbital with you. So if you have the value of L is equal to 3, you have S, P, D, F. So a subshell is a collection of the same, with a collection of orbitals with the same value of N, and L is referred to as a subshell. So the magnetic quantum number describes the orientation of the orbital in space. Is it oriented to the x-axis, y-axis, z-axis, and yes. So the value of ML are integers that depends on the value of the angular moment quantum number. Technically, this has something to do with the angles, all right? But since I know that quantum mechanics is a little bit complicated, I will not discuss it right here, but maybe in some other videos. So we have ml from negative L to positive L. So here are the values of the three quantum numbers, namely n equals 1. So the only value of the only value for L is 0, all right, because we have n minus 1. So the only suborbital there is s, all right, and yeah. So for n is 1, we only have one shell. So we only have s and nothing follows. All right. So it's only oriented in one direction. All right. So that is spherical. So that's why we get letter S for L equals 1. So we only have the spherical shape in here, just like the hydrogen atom. All right. So n equals 1 pertains to the hydrogen atom. So we have n equals 2. We only have 2. All right. So polar. All right. So P for polar. And we have 0 and 1. So we have spherical and polar. So there are two orientations that are shapes that are possible, spherical and polar. So you're gonna have several orientations that are possible, and later on we're gonna show that the shape depends on ml. So yeah, it follows. So it's from 3 n equals 3 to n equals 4. It is getting more complex. All right. So next, so here is how we arrange. All right. So we have n equals 1. So it doesn't have any any electrons. So it only have 1 or 2 electrons, and that can be carried by the s, okay, orbital. So we do not need for any allocation or place to allocate the electron. So technically, electrons has spin. It is used to specify the electron spin. It has something to do with the maintaining the, what do you call that? Forgot. Yeah, stability of the atom or the electrons. So there are two possible directions of spin. So we only have positive 1/2 and negative 1/2. So you can actually relate it to the magnets, right? Just like this. So you have positive 1/2 up and down, all right? So when we say the magnet is positive 1/2, so it is north and south, and if it's negative 1/2, the north pole is directed downward. So if a beam of atoms is split by a magnetic field, so it will actually result in a distribution of up and down deflection. So there are quantum numbers. The first one is the principal quantum number. The second one is the angular quantum number, which has something to do with the shape. And magnetic quantum number has something to do with the orientation. And these three are required to describe the atomic orbital. And we have the electron configuration. Like for example, if we have the principal quantum number n is equal to 2, we have 2px, and p there tells you that it has something to do with the angular momentum, and X here is for the um, magnetic quantum number. Alright, so it has something to do with the shape and orientation of the cloud where the electrons can be most probably be found. So right here, that's 2px, alright? So it is oriented in the x-axis. So we have the positive and the negative axis. So there is where we get the, yeah, so it is polar because it has two ends, alright? So ms is the electron spin. This is required to describe an electron in the atomic orbital. Alright, so for the first suborbital, alright, so principal quantum number is 2, but the angular momentum quantum number is equal to 0. The shape is spherical. So ml is equal 0, only one orientation possible, which is alright. So here are other p orbitals, and those are the things on how we use the quantum number. So I'm not going to deal with this anymore. Maybe I'm gonna present it in other topics and other videos, I mean. So in this part, we'll try to explain the valence electrons. All right. So these are actually the outermost electron of an atom. So we'll write valence here. All right. So I hope you're still with me. So valence electrons are the outermost electrons. Alright, so for example, we have a proton right here, and we know that it has an electron revolving in it. So this is actually an atom, or this is a hydrogen atom. And it is neutral, so it is electrically neutral when the number of proton is equivalent to the number of electron. So the atom is electrically neutral. Alright, so hence we call that it has only one electron. So this is what you call the valence electron. So for atoms, like those that are having many protons and many electrons, so the valence electron can actually be different from one another. Alright, so let's say for example, we are going to draw this in the subshell method, alright, or shell method. So we have the atom right here, which is positive, alright, so the only shell that is needed to accommodate the electron is only one. Alright, so n equals 1. So the electron is somewhere here, and that is our distance from the nucleus. So this is actually what Bohr is telling us. And the number of electrons that can occupy a shell is given by the formula 2 n raised to the power of 2, or 2n squared. So this energy level, so the first energy level, n equals 1, will contain a maximum of 2 electrons. So max equals 2 electrons. Alright, so these electrons can have different spins. Alright, so one might be going up and the other might be going down. Alright, so if we have 2 electrons right here, so we mean to say that this subshell or this shell is filled up. Shell is full. And in our case, in this case, we have valence electron is equivalent to 2. Alright. So I hope you understand that simple explanation about the valence electron. So here, if it has 2 electrons, so this is actually not hydrogen, but this is actually helium. Alright? So this is He. Alright, so this is hydrogen. So we can actually write the electron configuration. So this is 1s1. Alright, so because 1 here is the principal quantum number, and S here is the suborbital, and the number of electrons in that suborbital or the orientation is 1. So 1s1. Alright, so it's not paired up. Okay, so it's spherical. It's just spherical, you know. And here is 1s2. Alright, so that's the configuration. Okay, so we have 1 for the valence electron, and this one is the ground state. So this is the S is the lowest energy level. Alright, so you are going to look for the lowest energy level, alright, in counting the valence electron. Alright, so let's say for example, there are different letters right here, so you should look for the lowest energy level. So let's try to explain the valence and calculate the valence electron, and we'll try to show the valence electron of oxygen. So let's draw an oxygen atom. Alright, so I hope I can, but technically I'll just do a representation of oxygen. So oxygen, O2 actually, but let's try to use oxygen as is. Alright, so it has 8 protons. Alright, so to be neutral, it needs 8 electrons. Alright, yes, so according to the formula, we have to distribute the electron and a shell. The number of shell that we need is equivalent to the number of electrons. Alright, it's equivalent to 2 and squared. Alright, so we're gonna be dividing both sides by 2, so we're gonna have 8 all over 2 is equivalent to n squared. So we'll take the square root of that. 8 over 2, take the square root, is equal to 4. Alright, divided by, take the square root, so that is square root of 4, that is equivalent to 2, and that is equivalent to n. So we need 2 shells technically, so I'm gonna draw the oxygen right here. 1, 2, 3, or let's try another method, which is this one. I'll just draw a big circle. Oh no, that's not a circle at all. Alright, so let's draw one, and let's write 8p inside. So, and here are the 2 shells that use. Alright, so this is n equals 1 and n equals 2. Alright, so for n equals 1, we only have L equals n minus 1, and that is 0. So this is S, or meaning to say this is spherical. Alright, so it can contain 2 electrons, a maximum of 2 electrons. So we'll put the electrons inside this one. So E here and E here. Alright, so 1 is going up, 1 is going down, so it pairs up. So this shell is filled, but we still have 6 electrons. All right. So we have 6 electrons, and since it cannot go in n equals 1 or in the first shell, we're going to put it in the second subshell. All right. So we're gonna compute for L, and this is equivalent to n minus 1, which is 2 minus 1. We have n L equals 1. All right. So 1. So we have ML, or the magnetic quantum number, all right, which is from negative L, okay, to positive L. All right. So there you go, positive. So this is actually from negative 1, 0, and 1. All right. So we have negative 1, 0, and 1. All right. So there are 3. All right. So let's. So this is for the negative 1. This is for 0, and this is for positive 1. All right. So this one will contain 2 electrons. So E up, E down. All right. So that one is filled up. So we have E up. All right. E down. And we have this one. And we have this one. So technically 6 electrons are here. So we have 2 here, 2 here, and we have 2 here. All right, so we still have am I correct? Yes, I think. Yeah. There we go. So because we only have 6 electrons, 8 electrons, so we have 2 here. So if you add them together, you're gonna have 8 electrons, and the electrons are properly distributed in between among the shells. So we can actually use the knowledge to write, or in writing the electron configuration, and be able to find the valence electron of the oxygen. All right, so here we have 2 shells, so n is equals to 2, but we have to write from the start. So here we're gonna account for all of the electrons in this shell. So the VE of oxygen is equivalent to, or the electron configuration of oxygen rather, is equal to 1. So that is for the shell, n equals 1. So we have the S, and so it is filled, so 1s2. All right, so this is the subshell. All right, so, or L. All right, so L, or the what you call the quantum number L. All right, so and then next is you gonna put a comma. So I don't know if some are putting comma, some are not. All right, so we are going to account for all of the electrons in the second shell, n equals to 2. So you're gonna write 2 here for the shell, and basically it has the S with it, right? 2s1, 2s2, or 2p6. All right. So right here you can actually write 2s2 and 2p4, or actually 1s2. If I'm not mistaken, this is like this. All right, so 1s2, 2p6. Let's try. So you're right. So the correct one is the first that we have shown. So this one is the correct one. So I'll erase this. So forget about that. All right. So you can actually write it using the core system. All right. So by I'm gonna show you that. Yeah, that's what I can remember. All right. Basically, 1s2 is the electron configuration of helium. So here you can write He and put it in a bracket. All right. So yeah, just like this. So followed by 2s2, 2p4. All right. So s2 there is the spherical. So that is the lowest energy, a lower energy compared to 2p4. But nonetheless, they belong to the same shell. So these two are our valence electrons. So when you add them, it has a 6, all right? 6 Be. So that's why oxygen has 6 valence electrons. So before we go to chemical bonding, I just want to discuss the octet rule. So we have the octet rule. That means atoms are trying to get 8 valence electron. So 8 valence electron. Alright, so that's the octet rule. So it needs 8 valence electron to be stable. Alright, so that's oxygen is trying to grab, right? Two more electrons to get the valence electron equal to 8 and become stable. We can use the Lewis electron dot to show this particular example. So I have here um, uh, the oxygen, all right? So let's write the oxygen right here. Draw the oxygen right here. So it has 8 protons, all right? So the first shell is this one, all right? So it's not a circle. I'm sorry. So but the first shell has 2 electrons. So we have 2 here, all right? So there is a proper way on how you can put the Lewis dot structure. So you have second shell, so this is n equals 1, and here equals n equals 2. So we have um, 2 electrons there, 2 electrons down below. Alright, so let's just draw it again. Yeah. Alright. So we'll draw it again. So here is 8 protons, alright? So you know that is an oxygen. And there is n equals 1. And n equals... Oh, I'm sorry. N equals 2. Alright, so the second shell has 6. Alright. So you will see that something is missing. Alright. So if we need 8, so there are 2 more electrons that are vacant. Alright. So it needs to be filled up. So oxygen will try to grab 1 electron of hydrogen, put it right there, and another 1 here. Alright, so we have that one. So it will be able to complete the octet rule. That is, it will have 8 valence electrons. So that's how chemical bonding happens. So next is the type of bonds. All right. So we have. I'm gonna write type of chemical bond. First one is we have the ionic bond. All right. Next is what you call the covalent bond. All right. So these are the two types of bonds that we are going to encounter mostly in the study of chemistry. All right. And then we have the several types of reaction or of chemical reaction. Okay. Since the yep. So we write type of chemical reaction. So the first one is combination. Then decomposition. Then we have redox. Alright, so combination is when two products or two reactants form together. Alright, so it can be one direction, it can be reversible. So, but this one is one directional. So we have AB. They can be either exothermic or endothermic depending on the process. Okay, so let's deal more of that yeah, later. All right. So um, yeah, so there is another type of reaction which is a combination of these two. I forgot the name. Anyways, so you have like yeah, this will be reversed. So from A plus B or AB, it will be A plus B. Alright, so these are your reactants and these are your products. So there is another one, the combination. Alright, so which is like this. So it will go like AC plus DC, ano? PD. So these are the type of reaction. And redox, we're going to give more example about that. Alright, so let's clean that up. Let's clean this up and we'll go with balancing equation. Alright, so as easy as that. Balancing chemical equation. This is otherwise known as stoichiometry. Stoichiometry. All right. So just for example, you're gonna analyze a chemical reaction, like for example water. So these are existing in their diatomic form. So hydrogen plus oxygen. So both are gases. So you're gonna indicate the type of the reactants and products. All right. So let's just do that quickly. So the participating species here are both gases. So we're gonna write H2. All right. And here it's a gas. So you put G there plus O2, which is also a gas, put G here, and it will react, and it will actually uh, um, generate heat. All right, so there is heat liberated, so plus H. All right, so heat is liberated, but the signs are, yeah, you have to pay attention to for the sign. But right now, let's not focus on that, because what we are trying to say, trying to explain is focus on more on the balancing. All right, so it will react to form H2O, which is a liquid, so you can use L there. So you will see that there is a change in the form of the products and reactants. All right, from gas turn to liquid. All right, so you're gonna track and count the number of hydrogen in the left and the right side. So in the reactant side, you're gonna write R for the reactant. All right, and P for the product. All right, so we have the species. So we'll, I think I can write it here, R, because I'm gonna use this one as the interacting species. All right, so, or the participants. So we're gonna have H here. All right, so before and after. H and O. Alright, so reactants before, product after. Alright, so this is just the before, and this is the after. So if you guys think that there is some better way to illustrate this, you can actually help me. Alright, so before, there are only two hydrogen, which is known due to this subscript. All right, and before we only have O2, so we only have two oxygen before, but after you see that we still have two hydrogen, but we only have one oxygen, so it is not balanced. So all you have to do to balance this is to put coefficient before before the reactants or the product, just to keep it balanced. Okay, so here you will see that we have a problem in the number of oxygen. So 2 here before, so we need to make it 2, so we're gonna multiply it by 2. All right, so if you do it in the product side, you put 2 here. Alright, in doing so, you will see that 2 times 2 will be equal to 4. So if you multiply it by 2, this will be 4. This will be 2. So we do not have problems here because it's balanced. 2 before, and then afterwards it became 2. But we have problem right here because it became 4. So we need to multiply 2 right here. So 2 times 2 is 4, so there's no problem, so it's balanced. So we put 2 here. So the new equation, or the balanced equation that you can use in your stoichiometry or problems regarding the calculation of mass and moles of a certain product or reactant in a chemical reaction involving H2 and O2 is 2H2, all right? So that is a gas plus O2, which is also a gas, will yield 2H2O, which is a liquid. So this is your balance equation. So guys, I hope that you were able to learn a lot from this video. And if you think that we are lacking something, you can put your comments down below. And I know that this video needs more improvement. And you can help us okay? By putting your comments down below, and please at least give us a like and subscribe to our channel, and click the notification bell to get updated whenever we post new videos like this. Thank you guys, and thank you for watching in this long video of mine. Bye bye, see you next time.